Welcome to Chapter 5. In Chapter 4, we discussed what integrals are, how they arise, and how to compute them using the fundamental theorem of calculus. In particular, we saw that evaluating an integral requires us to find an antiderivative of the function that we are integrating. And all of Chapter 5 is devoted to that particular problem of finding antiderivatives. So in this first lecture, I want to begin by introducing some notation for antiderivatives, since we will be thinking about them so much, and then the bulk of the lecture will be devoted to one particular method for finding antiderivatives called substitution, or sometimes U-Substitution, for reasons that will become clear soon. But let's begin with the notation. Up until now, whenever we have wanted to write a statement about antiderivatives, we've had to do it in just ordinary natural language. We might say or write, an antiderivative of cosine x is sine x. And that's fine, of course, but it's nicer to have some kind of notation to make things more compact. And if we were inventing the subject from scratch, we might come up with our own notation. We might say, let's use this crazy green A to be our antiderivative operator. So we might say something like, the antiderivative of cosine x is sine x. Or maybe someone else would say, no, I don't like that notation. I think we should use a derivative operator with a lightning bolt through it to show that it's an antiderivative. So we'd say the antiderivative of cosine x is sine x. And maybe the proponents of this notation and this notation could fight it out. But you know what? The notation already exists, and it's better than either of these, but it would have looked very strange if I had introduced it before you met the fundamental theorem of calculus. So what is it? Well, since the whole reason we care about antiderivatives is because we use them to evaluate integrals, our notation for an antiderivative is actually going to be an integral sign, but without any boundaries of integration. And we also put a dx, or d, whatever variable we're working with, at the end. The integral sign and the dx go together like right and left parentheses, and the function that we want to integrate goes in between them. So to rewrite this statement in our new notation, an antiderivative of cosine x, we would write like this. And we can read this either as the antiderivative of cosine x, or we might just say the integral of cosine x. But we don't say from something to something. An integral like this without boundaries is often called an indefinite integral, as opposed to the integrals you have seen that do have boundaries, which are often called definite integrals. It's indefinite in a few senses. It's not asking for a particular weighted sum of infinitesimals. There's no sum at all. It's just asking us for the antiderivative of this function. It's also indefinite in another sense, and maybe this indefinite article gives the game away. Sure, sine x is an antiderivative of cosine x, but we know there are many others as well, and in fact, our antiderivative lemma from a few lectures ago tells us exactly what they are. The only antiderivatives, the complete list of antiderivatives of cosine x, are sine x plus any constant you want, and this plus c that I've tacked on is customary whenever we write down an indefinite integral like this. We find one antiderivative, and then we just say plus c as a reminder that an indefinite integral, an antiderivative, is really a whole family of functions. It's not just one function. This includes sine x plus 5, and sine x plus 97, and sine x plus pi, and so on and so forth. So that's the basic notation for antiderivatives. But please, please, please don't forget anything like this, where we don't have boundaries of integration, an indefinite integral in other words. That is a function, or rather a family of functions. This is in total contrast to something like this, the integral of cosine x as x runs from 0 to pi over 2. That is a definite integral. It is not some infinite family of functions. It is not even a function. A definite integral is a number. It is the result of a summation, an infinite sum of infinitesimals. In this particular case, of course, that's going to be this stuff, meaning we take an antiderivative of cosine, which is sine x, evaluate it at the top boundary, evaluate it at the bottom boundary, subtract, and we end up with 1. So an indefinite integral is a function, or rather a infinite family of functions. A definite integral is a number. Be sure you keep that distinction straight in your mind. But that is the notation we use for antiderivatives. So for example, we would write things like the integral of x cubed is x to the 4th over 4. And don't forget the constant. Or the integral of 1 over x is, of course, the logarithm of x plus the constant of integration, because it's that whole family of antiderivatives. or the integral of 1 over root 1 minus x squared. Do you remember what it is? You should. It is inverse sine of x plus your old friend, the constant. And that's the basic idea. We could use this notation, by the way, to reformulate something we discussed briefly in the last video. Namely, we said that antiderivatives obey the linearity properties. One of those properties is that you can take antiderivatives term by term. Well, we can either say that sentence, you can take antiderivatives term by term, or now we could write the indefinite integral of a sum is the sum of the indefinite integrals. Or we said last time, the antiderivative of a constant multiple of a function. Well, you can pull the constant out, then just take the antiderivative of the function that remains. That's kind of awkward in just ordinary language. But if we write it like this, it's going to be much clearer. So the integral, the indefinite integral of a constant multiple of a function, well, we can just pull the constant through the integral sign, like so, just like we could with the derivative operator. So these are the two linearity properties of indefinite integrals. We'll use them so frequently that after a while we won't even mention it. And as I said, we've already used them in the previous video. All I did here was translate them into symbols. But enough of them. Let's do a few more indefinite integrals. And let's do a few more where the answers aren't quite so obvious, like maybe this one, the integral of e to the 5x. What's an antiderivative of that? Well, hopefully that is obvious to you by now. This is one we can do with our little guess and adjust method. Pretty clear that it's going to be something like e to the 5x, but of course if we took the derivative of this thing, what would happen? We'd get e to the 5x, but then by the chain rule we'd get another 5. Well, that's not quite what I have here, so I need to balance that out with a fifth, so that will cancel with the 5 when I take the derivative. If I take the derivative of that, of course I get my e to the 5x times 5, and that 5 cancels with that 1/5, leaving me with exactly what I was aiming at, e to the 5x. So yay, this is an antiderivative, and I can get them all by putting the cherry on top, the c, the often forgotten constant of integration. So again, nothing new here, just getting used to this notation for indefinite integrals, for antiderivatives. How about the integral of secant squared of 2x? Ooh, that 2x throws it off, doesn't it? No, not by much. So we can once again rely on our old friend, the guess and adjust trick. It's secant squared of something, and we know an antiderivative of that. Tangent of the same old something. So we might think, okay, this is going to be something like tangent of our something, 2x, but is it right? Well, not quite, because if I took the derivative of that thing, I sure would get secant squared 2x, but then the chain rule would give me an extra 2. I don't want that 2, so I'm going to balance that out by sticking in a 1/2 up front, and that will do the job. When I take the derivative of this stuff on the right, the half just sits there, and then I take the derivative of tangent 2x, and I get secant squared 2x times 2, which cancels with the half, leaving me with just the plain old secant squared 2x, which I wanted. But wait, don't forget the constant. Good, now we've got it. Let's do one or two more of these guess and adjust examples. This one maybe is not quite so obvious. We want to integrate 1 over 2x plus 5. And if you've never seen one like this before, you might say, God, I don't really know what to do here. There's not an obvious antiderivative. But then hopefully after a few minutes, you might recognize, well, the problem is this reciprocal. It's 1 over something. Hey, wait a second. I know the integral of 1 over something. In fact, I did that right here. It's the natural logarithm of that something. So maybe the integral I'm looking for is something like log of 2x plus 5. Will that work? Well, if I take the derivative of that, what happens? I get 1 over 2x plus 5, which is good. Oh, but then I get a 2 because of the chain rule. Oh, well, that's easy. I just balance that out by putting a half right here. And that does it. So I can erase my question marks and put a festive constant of integration at the end. Good. Let's do one more by guess and adjust. The integral of 1 over 1 plus 4x squared. What's that? Oh, I know, it looks kind of like arctangent, because the derivative of arctangent of something is 1 over 1 plus the square of that something. Well, 4x squared is the square of the quantity 2x. So maybe this is going to be something like arctangent of 2x. Will that do the job? Well, if I take the derivative of this, I get 1 over 1 plus the square of my something. Yep, I square 2x and I get 4x squared. Oh, but the chain rule, once again, gives me a 2. So to balance that extra 2, I better put a half in here. And I'm sorry that I ended up with a half 3 times in a row. It's not always that way, of course. Sometimes it's a fifth or something else. But don't forget the constant, and we're done. Actually, despite the 3 consecutive 1/2, this was a nice example because people sometimes screw this up by thinking this should be arctangent of 4x. Be sure you understand why it's 2. All right, enough of those. Now you know our notation for antiderivatives, or indefinite integrals, as we like to say, and we can enter Chapter 5 proper, which is entirely about finding antiderivatives. So far, the only functions we have been able to integrate have been ones where we could come up with an antiderivative either just by staring at it and knowing our derivatives and doing it backwards, or by doing that little guess and adjust game. But there are a number of tricks of the trade for integrating functions that don't have such obvious antiderivatives, and you will meet the most common one today. That is the technique of substitution. Integration by substitution is sort of like doing the chain rule backwards. And just as the chain rule was the sort of thing where you had to do a few examples before you got completely used to it, but then it became pretty automatic, the same thing is true of substitution. Let's just jump right in and I will show you how it works with a specific example. The first one I show you may look mysterious, but I promise they will look less and less mysterious as we go on. Let's find the integral of 6x times sine of 3x squared plus 5. Ooh, that looks tricky. Can I think of an antiderivative of that off the top of my head? Probably not. Can I get it by guessing and adjusting? Well, you might actually be able to do that, and I encourage you to try, but I'm going to pretend for the moment that you can't, because this will be a good one to introduce U-substitution. There are often many ways to crack an integral. The way we would do this with U-substitution, the way we do any integral with U-substitution, is we look for something in the function we're trying to integrate. By the way, if I haven't said it before, the function we are trying to integrate is usually called the integrand. So if I ever say that, you'll know what I am talking about. So anyway, whatever the function is, we look in the integrand and see if we can find a piece, usually inside another function. Like here, sine of 3x squared plus 5. We look for such a piece inside another function whose derivative also appears in the integrand. And that's exactly what we have right here, because the derivative of this piece, the 3x squared plus 5 inside the sine function, its derivative is 6x, which also appears here. So to the practiced eye, this integral is calling out for U-substitution. Okay, but your eye is not so practiced yet. Don't worry, that will come in time. But what do we do once we have identified a piece like that, a piece inside a function whose derivative appears outside as well? Well, the trick is to set up a little dictionary between two languages. The language of x, which is what we have here, everything is expressed in terms of x, and the language of some new variable, which I'm going to call u. So I'm going to build my dictionary up here. The u, when we're doing U-substitution, is that little piece that appears in the integrand whose derivative also appears in the integrand. So in this case, I want to let u be 3x squared plus 5. So I will write that in my dictionary. That gives me a way to translate between x and u. So eventually I'm going to write a new integral that instead of having sine of 3x squared plus 5 is just going to have sine of u. Okay, but what else? I don't just need to translate x's. I have to worry about this dx, this little element of integration. I need to somehow translate from dx's to du's, because little changes in x, little infinitesimal changes of x, produce little infinitesimal changes in u, but I need to know exactly how they translate over. Well, that's really easy to figure out. How are du and dx related? Well, we know what their ratio is, du dx. That's just a derivative, the ratio of infinitesimals. Aha! And what is du dx? Well, if u is 3x squared plus 5, du dx must be 6x. Oh, that's nice. But what I really want is, just like my first statement in the dictionary where I have u in terms of x, what I really want is du in terms of dx. So let me just clear the fractions here. And when I do that, I end up with du is 6x dx. And that completes my little dictionary. And after doing a few of these problems, you'll eventually get to the point where you just write down u and then immediately you write down du without this intermediate stage. But I want to keep the training wheels on for the first few problems. The important point here, though, is we have du is 6x dx. And look, we have 6x dx in our integral. So that means that that whole stuff is going to turn into just plain old du, which is great because we said the other stuff is just going to be sine of u. So when I make all of those translations from my dictionary, let's see what we get. We have the integral of, maybe this will help if I color code it, this stuff right here, the sine of 3x squared plus 5. Well, 3x squared plus 5, that's u. So over here, that's going to become sine of u. Good, but we need to translate everything in our original integral over. And we've still got these pieces, 6x dx. But as we said a moment ago, 6x dx, well look, that translates to du in this new language. So all that 6x dx stuff comes over as du. And we're done. We've translated everything from the X language over to the U language. And that's great because even though the problem looked unwieldy in the X language, when we translate it into the U language, it looks really simple. What's the integral of sine? Well, of course, that is minus cosine. Although we're integrating with respect to U, so of course it's minus cosine of U. Now we can't stop there. We're not done because our original integral was expressed in terms of X. That means we need our answer to be in terms of X as well. The U is just some scaffolding we've put up to help us with this particular project of integrating this thing. We can't leave the scaffolding up at the end. We have to take it down and put it in terms of the original language. But that's easy. All I have to do is go back up to my dictionary. Minus cosine of u, well look, u is 3x squared plus 5. So making that substitution down here, this becomes minus cosine of 3x squared plus 5. But wait, we've forgotten something. What is it? The constant. Don't forget the constant of integration. Hooray, we've got it. We have successfully integrated this function and seen our first use of U-substitution. Let's do another example. Let's do the integral of x squared times secant squared of x cubed. Can we think of an antiderivative off the top of our heads? Probably not. Can we get this by guessing and adjusting? Quite possibly, and I encourage you to try. But even if you try and succeed, I want you to see how we would do this using U-substitution because this is a good candidate for it. Why is it a good candidate for it? Can I see something here in the integrand whose derivative appears elsewhere? You might say, oh, it's real close. X cubed, if I take the derivative of that, I get 3x squared. Ooh, so close, but not quite. I've got x squared. Well, guess what? Just like the guess and adjust trick, that extra factor, that constant factor of 3 really doesn't matter. As you'll see in a moment, we can always make a little adjustment at the end to fix that. So actually, the fact that we're only off by a constant factor, the derivative of x cubed is 3x squared, is good enough for our purposes. This looks like a great candidate for u. So let's set up a little dictionary. We're going to let u be x cubed. So that gives me the relationship between u and x. Now I need to relate du and dx, which I get by looking at du dx, which is just a derivative. If u is x cubed, then du dx, of course, is 3x squared. So to get the relationship I want, I clear the fractions as always, and I get du is 3x squared dx. And my dictionary is complete. And as I said before, after you've done a few of these, you will go straight from this step to writing down du is 3x squared dx. But I want to keep that extra step in there just one or two more times so that you get a feel for what is actually going on under the hood. Okay, so using this dictionary, we just need to translate everything from the X language over into the U language. Well, what do we have? We've got this secant squared of x cubed. Well, since x cubed is u, that translates over as secant squared of u. And what's left? I've still got an x squared and a dx. What can I say about x squared dx? Oh, it's so close to my expression for du. Look at this equation right here. 3x squared dx is du. But look, that means x squared dx. What's that? We'll divide both sides by 3, and we see that x squared dx is going to be du divided by 3, or in other words, a third of du. So let me go ahead and put that in here. And I'm going to split those factors up. I'm going to put the 1/3 in the beginning and the du right here. But the important thing here is our translation is complete. Everything was in x here. Now everything is in the u language. And why did I go ahead and split those up? Well, we like to have constants up front, but hey, this is an opportunity to use one of those linearity properties of indefinite integrals that I mentioned a moment ago. I've got a constant multiple of this function. That means I can go ahead and pull that through the integral sign if I wish, which I do. Great. Now this is an easy integral. Everybody knows that an antiderivative of secant squared is tangent, but this was an integral with respect to u, so this is going to be tangent of u. And don't forget that factor of 1/3 that we had sitting outside the integral. That, of course, has to be carried along. And so we're basically done, except, of course, we have to translate back into the x language. We started by integrating a function with respect to x. We'd better get a function of x at the end. But anyway, that step is always trivial because we have a dictionary after all. What is u? It's x cubed. So 1/3 tangent of u is 1/3 tangent x cubed plus, of course, the constant of integration. And we are done. The derivative of this function for any value of c is going to be x squared secant squared x cubed. And as I've said in previous videos, one nice thing about integration is when you come up with an antiderivative, you can always check your work just by taking its derivative and verifying that you get what you are supposed to get. Okay, this isn't so bad, you see. Let's do a third example. Let's integrate xe to the minus x squared plus 5x squared times cosine 2x cubed. Now, I'm going to do this integral two different ways, and I think you'll have something to learn from both methods. The first way I want to do it is very systematically, spelling out everything. Well, if we do that, the first thing we might notice is that this integrand really is too complicated to handle all at once. But that's okay. It's the sum of two simpler functions, and we know that the integral of a sum is the sum of the integrals. That is one of our two linearity properties of integrals. The other linearity property of integrals tells us that if I have a constant multiple of a function that I'm integrating, I can pull it through the integral sign, like I did with that 5. So to sum up what we've done so far, our original integral is equal to the sum of these integrals by the linearity properties of integration. So in one step, you might say we've made things harder because we've gone from one integral to two integrals, but on the other hand, it's easier because each individual integral looks fairly straightforward. In fact, by now, on example 3, you should start to see that each one of these integrals is something we can get with U-substitution. Before we actually carry it out, you might notice that in this first one, if we made this exponent minus x squared, if we took that as u, well, the derivative minus 2x is almost what we get here in the integrand. It's only off by that constant factor of minus 2. So that should work here. Meanwhile, on this integral, we have cosine of 2x cubed. So if we took 2x cubed as our u, well, the derivative of that bit is 6x squared. Oh, that's good because we have an x squared here, which again is only off by a constant factor. So that should work as well. So let's carry that out. Let's see. How am I going to notate this? Let's try this. I'll put the dictionaries for each one in different colors. So for this first integral, we're going to let u be minus x squared. And remember how I said on the earlier examples that after a few practice problems, you'll eventually be comfortable going from u straight to du without having to first write down du dx? Let's start working our way towards that now. The thing to remember is that we can get to du always, in any case, by looking at du dx, that derivative, and then just multiplying by dx. This is obvious, right? The dx's just cancel and we get du is equal to du. So it's like we're factoring the du into two pieces, and we can always do that. Anyway, in this case, if u is minus x squared, then du dx, the derivative of u with respect to x, is of course minus 2x, and we have our expression for du. It's minus 2x dx. Ultimately, what we're doing is just taking the derivative of that guy and then tacking dx on the end. And let's go ahead and convert that integral over into the u language. When we do that, e to the minus x squared, of course, just becomes e to the u, and what's left over? X dx. Well, what does the x dx translate to? Well, look in our second entry in our dictionary. X dx, well, if we divide both sides of that entry by minus 2, that is going to be minus a half of du, like so. And of course, this minus a half is a constant factor of the integrand, so I can pull it through the integral. And that kind of step is something that will become so automatic to you that after a while, you'll just look at something like this and say, oh, x dx, I see, that's minus a half du. I'm going to go ahead and put the minus half out front, du. But anyway, this is going to be very easy, but let's finish it off in a moment. Let's go and convert this other integral into the u language. A different u language since we'll have a different u. In this case, we said we're going to let u be 2x cubed, like so. And what can we say about du? Well, remember how we just thought about it. Du is the same thing as du dx times dx. We've just essentially factored our du into a more convenient form. And if u is 2x cubed, then du dx, the derivative of u with respect to x, must be 6x squared. Good, now we have our complete dictionary. So let's translate this integral into the u language, remembering to pull that factor of 5 down as well. And let's see what we've got. Cosine 2x cubed. Well, of course, that is going to become cosine of u. And what's left? The x squared dx. Well, what can we do with that? We look at our second entry in the dictionary. Aha, x squared dx. If I divide both sides by 6, I see that that stuff is going to be 1/6 of du. So I'll put that down here. There's my 6th and there's my du. And once again, I'm going to pull this constant factor of a 6th through the integral sign. Good. And so we have reduced this original complicated looking integral into the sum of two really simple integrals. In the first one, I have that factor of -1/2, and then the integral of e to the u is, of course, e to the u, but I need to translate everything back into the original x language. Well, this u was -x squared. So making that substitution, we get a -x squared. Now let's not do that, because some of you might be saying, hey, don't forget the constant. Okay, I'll put it in for now. Plus c. In fact, let's say plus c sub 1, because there are going to be two constants, one for this integral and one for this integral. I'm going to end up combining them at the end, but I just want to make sure this is clear, so I'll do this carefully once. So c1, where c1 can be any real number you please. All right, let's keep going. To that, we add 5/6 of the integral of cosine u with respect to u. Well, that, of course, is sine u, but this u, my green u, is 2x cubed. And of course, for this integral as well, I should include a constant of integration, so I'll call that one c2. Now let's think about this stuff for a sec. In one sense, we're done. But you might say, hey, that's kind of weird that we have two constants of integration. We really don't. We really only have one. Because first, let me rearrange this stuff a little bit. Like this. I just swapped the positions of those two terms. So my claim is that the integral of this original function is -1/2 e to the -x squared plus 5/6 sine 2x cubed plus c1 plus c2, where c1 and c2 can be any real constants whatsoever. But look, there's no point having two separate constants like that. If you say, well, this one, let's let it be 2, and this one, let it be 7. Well, all right, but why not just have one constant and call it 9? Or if this one is 3 and this one is -17, you don't need them. You just have one constant and call it -14. So we can combine those into a single constant and say the integral of this thing is all this stuff, the core function, plus plain old c, where c can be any real constant. Make that singular whatsoever. And that's that. We're done. As always, we could check our work by taking the derivative of this thing and making sure that it really is equal to the original integrand. I'll leave it to you to do that. All right, you see that wasn't too bad. Just using U-substitution and those linearity properties a few times. But I said I wanted to do this one two different ways. This was the pretty careful way. Now let's do it much more directly. For this second solution, I want to show you how we can just write down an antiderivative of this all at once we are comfortable with the idea of guessing and adjusting in our heads. If you're not comfortable with that yet, don't worry about it. You can always write these out the long way. But I want you to see how it's done. Okay, I'm looking for an antiderivative of all this stuff. I know I can do antiderivatives term by term, so I'm just going to concentrate on this first term for now and see if I can come up with an antiderivative of that term all by itself. Well, this looks like a job for substitution, and we could do that explicit substitution like we just did. That's fine. But often, not always, but often when we do substitution, once we've recognized the thing that I want to substitute for, whose derivative shows up elsewhere, it kind of gives me a hint of what the antiderivative is going to look like. This x shows up in the du, right? I'm going to get the x dx. That's sort of what my du is, except for a constant factor. And the rest of it turned out to be basically e to the u. So maybe my antiderivative should look something like e to the -x squared, e to the whatever it was. Will this work? Now I just want to think about it. Take the derivative of this thing in my head and see if it comes out to this stuff. Well, if I take the derivative of that, the chain rule tells me I get the thing itself back times minus 2x. Well, the x I really like because I have that right here. Oh, but I don't want that minus 2. I need something to cancel out with that minus 2. Well, that's fine. I could just put a minus half there, and that should do the job. Because if I took the derivative of this stuff, the minus half would just sit there, while this would give me e to the minus x squared times minus 2x. That would give me my x, and the minus 2 would cancel with that. Perfect. So I know this will work, and to celebrate, I'm going to get rid of the blue and rewrite this in black. Okay, now I have to move on to the next term, because, as we said, antiderivatives I can take term by term. Well, let's see. As I said before, candidates for substitution are often also candidates for guess and adjust. This, as we've said before, is a good candidate for substitution, because if this is u, then the rest of the stuff out here becomes basically du, up to a constant factor. So that makes me think that maybe an antiderivative of that term would be something like sine of 2x cubed. Because when I take the derivative of sine of whatever, I get cosine of whatever. But of course, I also have to contend with the chain rule. The derivative of this stuff is cosine 2x cubed times the derivative of the inside, which is going to be 6x squared. Ooh, that's almost what I have here, but not quite. I get 6x squared when I take the derivative, not 5x squared. Well, how do I turn a 6 into a 5? Multiply it by 5/6, of course. So will that make it balance? It should. The 5/6 just sits there when I take the derivative of the whole thing. And the derivative of this function is, as we said, cosine 2x cubed times 6x squared. The 6 cancels with that 6 downstairs, leaving me with 5x squared. Perfect. That does the job. So let's put that in black too. Well, I'll be damned. We did it in one shot. And don't forget the constant. But I repeat, if you don't like doing that in your head, don't bother in the beginning. After a while, you'll want to, because you'll be sick of writing down all those u's and du's and so forth. But very frequently, for simple substitutions, just playing the guess and adjust game will get you where you need to go. So try it both ways on problems in the homework and see what you do. And you'll see which is most comfortable initially. And after doing this stuff for a few weeks or months, you may switch from writing everything out explicitly to just doing stuff in your head. Either way is good. Okay, one thing we have not done yet is a definite integral that involves substitution. The only thing that changes there is that we will need to be careful to translate the boundaries of integration from the x language to the u language as well. So to see what I mean, we'll do our fourth example, where we will integrate this rational function x over the cube of x squared plus 2. But let's make it a definite integral. Let's integrate this guy from minus 2 to minus 1. Now, can you come up with an antiderivative by just staring at it or doing a guess and adjustment? Maybe, but probably not at this point. And frankly, even if you can, I want to write out a careful substitution. This one's sufficiently messy that you could mess yourself up trying to do a guess and adjust. But is it even a candidate for substitution? Is it a likely candidate? A little thought shows that it is, because look at the denominator. We're cubing x squared plus 2. Well, x squared plus 2 would be a good candidate for u, because its derivative, 2x, basically appears in the integrand. We've got an x there. Sure, we don't have a 2, but those constant factors don't really matter. We can always adjust for those, as we have already seen. So that means that the x dx is basically going to turn out to be du with some constant factor that doesn't matter. And downstairs we'll have u cubed. So the question is, can I integrate 1 over u cubed? Well, sure, that's u to the minus 3. That's a power function. We know how to deal with those. But let's not get ahead of ourselves. It looks like this is going to work, so let's set up a dictionary and follow it through. If we let u be x squared plus 2, then what's du going to be? Well, as we said, du could always be factored as du dx times dx, because obviously those dx's cancel, and du dx is something we can compute. If u is x squared plus 2, then u's derivative with respect to x is 2x, and we have our complete dictionary. So now let's do our translation. Everything starts out as we did before. Downstairs, instead of having x squared plus 2 quantity cubed, we will just have u cubed. And what's left? We've got x dx. Well, coming up to the second entry in our dictionary, we see that x dx, when we divide both sides by 2, is going to be half du. So I'll put that down here as half du. Notice that I went ahead and pulled the half through the integral sign, just using one of those linearity properties again. Constant factors can be pulled through the integral sign. And you might be tempted to just start hammering away at this and get the antiderivative, but wait. There's one thing we haven't done yet. This is a definite integral, a number. We're adding up this weighted sum of infinitesimals. We're adding all these things up as x runs from -2 until x reaches -1. But we're doing everything in terms of the U language here. So we need to be able to say as U runs from something to something. That's not going to be -2 and -1 anymore. How do we figure out what those new boundaries are going to be? Well, of course, we use our dictionary. When x is -2, well, what's U going to be? U is x squared plus 2. So that would be, if x is -2, U is going to be the square of -2, which is 4, plus 2. So we're going to end up with 6 for that lower boundary with respect to U. And we'll get the upper boundary in the exact same way. Initially, we had when x was -1. Well, when x is -1, what's U? That would be the square of -1, which is 1, plus 2. So U, in that case, would be 3. And now our translation is complete. So let's go ahead and finish it off. We'll carry the half down. And this will be easier to see maybe if we rewrite the integrand as U to the -3 power, which makes it explicit that this is a power function. So integrating it, taking its antiderivative, is easy. It's the usual thing. We raise the power by 1, which will give us -2, and divide by the new power, which is -2. And we are integrating, and of course we need to bring our boundaries down to our bracket, 6 and 3, and now we just have some arithmetic to do. The arithmetic will be easier if I take this factor of -1/2 and pull it through the bracket to get -1/4. We saw earlier that we can always do that with constant factors in the bracket as well. And it might also be easier to see if we rewrote this U to the -2 as 1 over U squared. And now let's see. When U is 3, this stuff becomes 1 over 9. And when U is 6, it is 1 over 36. Get a common denominator of 36, do a little arithmetic, and we reach a final answer of -1 over 48. And notice there's nothing to translate back because we don't have something here in the U language. This is just a number. It's the result of this sum. This sum is equal to this. These are all just numbers. This is a number that's equal to this number, which is equal to this number, and so on and so forth, which is this number. It's not a function of U or a function of X. It's just a number. So that's the end of the game. The result of this infinite sum of infinitesimals is -1 over 48. And the key thing to remember here is that when we did the integration and we did a substitution, we had to translate not only the function and the dx, but the boundaries of integration as well. Good. Let's do another example of a definite integral involving substitution. A pretty easy one. We want to integrate 5x times cosine x squared as x runs from 0 to the square root of pi. Now here we are, only at our 5th example, but this one should already be screaming out to you for substitution. Because when you see that cosine x squared and you see the derivative of that inner function, or at least the derivative up to a constant factor, sure it's 5x instead of 2x, but big deal, we can adjust that at the end, you should recognize this is a job for substitution. So let's carry it out. We're going to let u be x squared. So what's du going to be? Well, one last time I will write out that it's factored as du dx times dx, because the dx's cancel, making this an obvious equality. But du dx is something we can compute. U is x squared, so the derivative of u with respect to x is 2x. Our dictionary is complete, and our translation begins. Of course, cosine of x squared comes over as cosine of u. The stuff that's left, 5x dx. What's that going to be? Well, to get 5x dx, I would have to multiply this junk, the 2x dx, by 5 halves. That would turn it into 5x dx, but that means I would have to multiply the du by 5/2. So the 5x dx is going to be 5/2 times du. And note that I've gone ahead and pulled the 5/2 through the integral. By the way, of course, you could have pulled this initial 5 through the integral and just carried it along for the ride. That would be fine too. Am I done? Should I start integrating? Wait. We need to translate the boundaries of integration over as well. Here we are summing this stuff up as x runs from 0 to when x is square root of pi. Well, when x is 0, what is u? Well, u is the square of x. The square of 0 is, of course, still 0. And what about up here? Well, when x is the square root of pi, what's u? U is the square of x. So when we square the square root of pi, we get pi for our upper boundary. Well, this integral is a piece of cake. Let's carry the 5/2 over. An antiderivative of cosine is, of course, sine. And we are running from 0 to pi because everything is in terms of u. Well, that's 5/2 of sine pi. What's that? If we rotate through pi, the y-coordinate is 0. So that's 0 minus sine of 0. Well, if we don't rotate at all, the y-coordinate is, of course, also 0. So 0 minus 0 is 0, and you multiply it by 5/2, and it's still 0, which is the value of this original definite integral. You getting the hang of this? It's not too hard. Ask anyone who has taken calculus what their favorite integration technique is, and they will almost always tell you substitution, because it occurs so frequently, and it's really easy once you get a hang of it. But let's do another example or two. So example 6 will be the integral of e to the x over the quantity e to the x plus 4 as x runs from minus log 3 to log 3. So once again, it's a definite integral. It's a number. We're going to end up with just a real number. But to do that, we're going to need to find an antiderivative of this thing, which you're probably not going to think of off the top of your head. But if we do some substitution, we'll put it in a form where it will be easy. After a little hard staring at this thing, you might think, I see it. The thing is riddled with e to the x's, and I know e to the x is its own derivative. If I took the whole denominator as u, then du, the derivative of that thing, times dx, would just be e to the x dx, which is all that's left over. So the denominator's derivative is e to the x, which appears as a factor of the integrand. Let's try it. Sometimes you may not even be 100% that a given substitution will work out, but you can always try, mess around, and see what you can do. In this case, though, it should work out with no problem. So as I said, we're going to let u be e to the x plus 4. So what's du going to be? Well, as we said, I'm not even going to write it down this time, but I'll still say it. We factor du as du dx times dx. Well, du dx, if this is u, is just going to be plain old e to the x, and then we have times dx. So there's our complete dictionary. Now we will use it to translate everything over into the u language. What happens with this fraction? Well, the denominator becomes u. E to the x dx, well, that we said is just du. And I deliberately put it up here just to show you that it's not uncommon for people to stick the du on top of a fraction if the numerator is just 1. I'll try to keep it down in its customary place, especially in the beginning, but it's something you will encounter in practice, so nothing deep about it. Anyway, so we've translated all this stuff over into u, but we're doing a definite integral. We're adding things up, starting when x is minus log 3 and stopping when x is log 3. We need to translate that into u. Well, when x is minus log 3, what's u going to be? U is e raised to the power of x plus 4, which is going to be Wait, some of you need a review, don't you? Okay, hold on. Quick review down here under the green line. First, what does log of anything, log of green star, what does it mean? By definition, it's the power you must raise e to get green star, right? You know that. Everyone knows that, I hope. So that has an important consequence. What is e to the log of anything? Well, think it through. What does this mean? This means that we are taking the number e and we are raising it to some power. To what power are we raising e? We are raising e to the power you have to raise e to get star. So of course, what you get is star. And this is one of the key properties of exponential functions and logarithms. While we're here, I'll remind you that it works the other way around. What's the log of e to the star power? Well, what does this mean? This is the power we have to raise e to get e to the star. Well, that power is obviously star. And these are the so-called inverse properties of logarithm. We use them all the time. There are other important properties of logarithms, but the most important of the remaining ones by far concerns expressions of this form. Log of something, a, raised to some other power, b. This can be rewritten in another form. What is it? Do you know it? It should be as automatic to you as 2 plus 3 is 5. I hope you know what it is, but if you don't, I will tell you in a moment. And if you do, you might not remember why it is so. So I'm going to go ahead and rederive it so that everyone gets something out of this review, including those who know the formal rule, but maybe don't know where it comes from. So here's where it comes from. It comes from this inverse property, which of course is so obvious. So let's see. What I'm going to do is to first just concentrate on the a, the base of that expression inside the logarithm. And I'm going to rewrite it in a different form. Just the a, I know I can rewrite as e to the log a. So let me get rid of that equal sign for now. But I've just rewritten the a itself as e to the log a. By this first inverse property, I know that e to the log a is a. So, okay, so far so good. And now all I'm going to do is carry the rest of the stuff over. So I'm taking my a in this new form. What am I doing? I raise it to the power of b, and then I take the logarithm of the whole thing. And so those two expressions are certainly equal to one another, because all I have done is replace the a by something that is equal to it. And notice that the move I'm doing here, replacing something simple by something that is momentarily more complicated, but will set me up, get me into a position for something I really like in a moment, that's kind of analogous to what we were doing with the u du in our substitution, where we factored du into something that momentarily seemed more complicated, du dx times dx, but it got us something we wanted. Anyway, why does this give me something I want? Well, now I can use inside these big parentheses in the argument of the logarithm, I'm going to use a basic property of exponents. Everybody knows that a to the b raised to the c power is a to the b times c. You multiply those exponents. I'm going to use that property here. I'm going to multiply those two exponents because remember, log a is just a constant. So I've got this constant times this constant, and when I multiply them together, I get e to the b times log a by this basic property of exponents, which is so simple that I'm now going to erase it. Okay, now look at this. What have I got? Log of e to something. Hey, that looks familiar. That's just one of our inverse properties. Log of e to the something is the something, because we're saying, what's the power I have to raise e to get e to the b log a? Well, of course, that is just b log a. And this was the expression I was looking for. Log of a raised to the power of b is equal to, let me get rid of all that scaffolding, b log a. Formally, all we're doing is when I have log of something to the something, we take the power and pull it down in front of the logarithm. This is probably the most important property of logarithms because it effectively turns exponents into multiplicative factors. It reduces exponentiation to multiplication. That is why we use this when we're solving any kind of equation where the variable is in the exponent. Logarithms help us pull the exponent, in that case, down to the ground where we can get to it. Anyway, that's enough logarithm review. I'll leave that up for a second because I'm going to need to refer to it up here. Where were we before we retreated down into the basement? Oh yes, we were doing this integral and we were translating everything over, and the last thing we were doing was working with the boundaries of integration. And we said when x was minus log 3, u was going to be e to the minus log 3 plus 4. Well, what's that? Well, it takes a couple of steps to reduce this to a simpler form, but it's easy. The first one, we've got negative log 3. Well, to put that in a form that'll be nicer to work with, I just use this property down here of logarithms, but I'm using it backwards. Not only can we pull exponents down to the ground like that, but when they're on the ground, we can push them up into the exponent. So that means I could rewrite e to the minus log 3 as e to the log of 3 to the minus 1 power. Now, why would I do that? because now it's in the form where I can use these inverse properties. E to the log of anything is that anything. So e to the log of 3 to the minus 1 is 3 to the minus 1, which of course by definition is a third. And when you add a third to 4, which is 12 thirds, you get 13 thirds. So that is going to be our lower boundary of integration. And that way of thinking that we just dealt with right there, which involved basic properties of logarithms and exponents and negative exponents and all that, you should be very, very comfortable with that. And if you're not, you need to get comfortable with that. It's okay when you identify holes in your foundations, but you do need to repair them. You can't just let them sit there. Okay, anyway, we still have to get the upper boundary of integration, which is a little more straightforward, because when x is log 3, u is e to the x, so e to the log 3, which is 3, plus 4, so we end up with 7. Okay, that's an easy integral, because the integral of the reciprocal function is the logarithm function, and we are evaluating this thing with the help of the fundamental theorem as u runs from 13 thirds to 7. So that's going to be log of 7 minus log of 13 thirds. But don't leave it like that. You know some basic properties of logarithms. We've reviewed the main ones right here, but there are other important ones as well, and we can use one to simplify here. Just as this property essentially shows us that logarithms turn exponentiation into multiplication, logarithms do that sort of thing with other operations as well. It's nice. They make each operation simpler. Not only does exponentiation become multiplication, but we also have that logs do something nice to multiplication. It essentially reduces multiplication to addition. The log of a times b is the log of a plus the log of b. And similarly, logarithms do something nice to division. They effectively turn division into subtraction, because log of a over b becomes log of a minus log of b. I will leave the derivations of those two things to you, but they're actually pretty easy to derive. If you understood the derivation of this property, you can get these ones with very similar proofs. These ones don't get used as frequently as this one or the inverse properties, but they definitely have their uses, and one we can see right here in cleaning this up. We've got the log of something minus the log of something. Well, if you remember, oh yeah, logs turn division into subtraction. Log a minus log b, that's the same thing as log of a over b. So that means this thing is log of 7 over 13 thirds, which of course is the same thing as saying log of, well, dividing by 13 thirds is like multiplying the 7 by 3/13, so that is the log of 21/13, and that's that. This is just a number, namely the exact value of this definite integral. Okay, I hope the logarithm review helped a little bit. Let's do one last example before we call it a day. This last one is going to be trickier than the previous ones. The integral of 1 over the product of the square root of x and the quantity x plus 1. And we're doing that as x runs from 1 to 3. Now this is a tricky integral, but I wanted to end with a tricky one to emphasize that sometimes you're going to be faced with integrals, even after you've learned a bunch of techniques, where you won't quite be able to figure out what's going on. And after trying this and trying that and nothing works, you may end up resorting to desperate Hail Mary substitutions, just to see if you can get something by luck. Well, this might be an example where you might end up doing something like that, where a surprising substitution, maybe taken out of desperation, will ultimately crack this integral. It's not really like the other ones where we were able to see immediately, aha, here's a little piece of the integrand whose derivative shows up elsewhere, so substitution will do the job. Doesn't quite seem to be the case here, but nonetheless, it will do the job. So you will have to imagine we've already spent 10 minutes staring at this thing and being frustrated, and eventually we say, oh my goodness, let's just try something. What if we let u be the square root of x? I mean, the square root of x is here, but is that going to help? And at first thought you might think, probably not. I mean, what would du be? Du is, of course, du dx times dx, and du dx here, well, what's the derivative of square root of x? Well, everybody knows that's 1 over 2 root x dx. I'll throw that in as well. Is that actually going to help? I mean, if that's u, du just doesn't seem to be anywhere in sight. Although, wait a second, this part of du actually does show up here. I mean, 1 over root x dx, we have that. So in a way, we kind of have the du, but then where's the u? Oh my goodness, it's actually here, because x plus 1, well, I could think of the x as u squared. Is that going to work? Well, let's see. So using this sort of sneaky, sort of lucky way of doing things, we could start with the 1 over square root of x dx, and we'd say, well, all right, 1 over square root of dx is here. I'd have to multiply the right-hand side by 2 to get it. So all that junk over here is going to be 2 du, which is really 2 du, and I've just pulled the 2 through the integral sign. But what does that leave me with? Well, it leaves me with 1 over x plus 1. But if the square root of x is u, x, we said, is the square root squared, so that would be u squared. So I could think of all that stuff as 1 over u squared plus 1. If I pop that in here, we get 1 over u squared plus 1. And I wrote those in the opposite order to make it a little more suggestive of something, namely, oh, I know the antiderivative of that guy. That is arctangent. We'll use that in a few moments. But anyway, we still need to translate our boundaries over. We're integrating as x runs from 1 to 3. Well, when x is 1, u is the square root of x. Square root of 1 is 1. And for our upper boundary, when x is 3, well, u is the square root of x, so u is going to be the square root of 3. And now we are in business. This is going to be 2 times that integral. Well, an antiderivative of 1 over 1 plus u squared is arctangent of u. And on our bracket, we will have 1 and root 3. So, of course, that's going to be 2 times arctangent of root 3 minus arctangent of 1. Now, again, these should be things that are pretty much automatic to you at this point, like those logarithmic properties. But if they aren't, these are values you can read off of the 2 special triangles we use again and again and again and again throughout trigonometry. The half square, also known as a right isosceles triangle, and the half equilateral triangle, also known as a 30, 60, 90 triangle. The ratios on these triangles should certainly be well known to you. The half square is obvious. If we call the sides of the square 1, well then by the Pythagorean theorem, immediately the hypotenuse is root 2. And of course, the angles are both 45 degrees, and of course the right angle in the corner. Meanwhile, in the 30, 60, 90 triangle, if we call the short side 1, well that means each side of the equilateral triangle is 2, so that means the hypotenuse is 2, which means that by the Pythagorean theorem, I can compute the remaining leg, which of course will be the square root of 3. And from these 2 triangles, I can read off the sines and cosines and tangents and secants and cosecants and all that stuff for any of these 3 angles, 30, 60, or 45. Well, the arctangent of root 3. What's an angle whose tangent is root 3? It's 60 degrees because the opposite is root 3 and the adjacent is 1. So the tangent of 60 degrees is root 3 over 1, which is root 3. So the arctangent of root 3 is a 60-degree angle, but of course we do everything in radians, so that is going to be pi over 3. And the arctangent of 1 is pi over 4. That's one you should know, like 5 times 4 is 20, because pi over 4 is 45 degrees. And of course, the tangent of 45 degrees is 1, because the opposite and adjacent are the same. So opposite over adjacent is 1. Do a little arithmetic here, and you get pi over 6. And that is that. Whew! It's been an eventful lecture. You learned about notation for antiderivatives, you learned how to do substitution in indefinite or definite integrals, and you even got to review a little bit about logarithms and basic trigonometry. Good. I will see you next time. Goodbye.